Okay, this is for section 5.3 called Polynomial Functions. Remember, when they had the word polynomial function, remember, you can tell a function by the vertical line test. If no 2 points line up and down on your graph, then it is a function. The first thing the author defines is a polynomial expression in one variable. Now notice it doesn't say equation, so there's not an equal sign. It's just a polynomial expression in one variable. Okay, and it's written this way. Okay, you might have to look up here for a minute. It's a sub n. Now, when you write that, write it as a subscript. Don't write it a n like that. It's a subscript, a sub n. That's like the coefficient x to the n power plus a sub n minus 1 x to the n minus 1 power plus, and then we're going to leave out some terms, so put in the plus dot dot dot, and then another plus sign. You need a plus sign at both ends there, and then a sub 1 to the times x to the first power plus a sub 0. So like I could write this as like, you know, I could make up one and say this is like 5x to the 4th plus 18 x to the 3rd plus, and then I leave out terms, and I'm just going to make up 3x minus 6. So that would be a polynomial expression, and I'd fill in all the terms in between. The a's in front represent coefficients. Okay, so all these a's represent the numbers in front. Okay, there's some qualifications here. The a sub n cannot equal 0. Okay, all the a sub, look how I write this, all the a sub i's, okay, are elements of the real number systems. So all those coefficients have to be real numbers. So what would the only exception be? If they were not real numbers, they would be imaginaries. The I values, like you cannot have a coefficient that's like 5i. That wouldn't work. They have to be, this symbol, this one is the Greek letter epsilon, means is an element of the set of real numbers. Okay, and n is a non-negative integer. So basically that's saying your exponents cannot be a negative integer. Like you could not have -3 as an exponent for it to be a polynomial expression. Okay? Okay, so now they will give you some problems like this with that definition. State the degree, and they talked about that earlier. State the degree and the leading coefficient. The leading coefficient means the number in front of that highest degree term of each polynomial in one variable. If it is not a polynomial in one variable, explain why. And that's just a pretty basic explanation. Okay, so let's go through some examples with those directions. Okay, so if I gave you a -2a to the 3rd plus a minus 1 over a squared. First, is that a polynomial expression in one variable? how would you rewrite that term? Bring that a up, and it'd be a to what power? A to the negative 2 power. Can we have a negative exponent? No. So this one is not a polynomial. For this part, you just say polynomial. That's good enough. Not a polynomial, and our reason is that would be written as a to the negative 2. We can't have a negative exponent. That's good enough. Okay. Second example. Say we have x to the 5th plus x to the 2nd minus 8. Does that satisfy the definition? Yes. So that is a polynomial. If it is a polynomial, they want you to give the degree. Yep. So the degree is 5. Yep. We're just going to use LC for leading coefficient. The number in front of that is 1. Okay. Mn plus 3m minus 7n. How many variables are in there? 2. So not a polynomial. It's got 2 variables in it. 2 variables, m and n. That throws that off. Fourth example, 11 minus 5c plus 2c to the 6th minus 4c to the 3rd. Yes. Degree. Yep, the highest exponent is a 6. And the LC leading coefficient is 2. Okay, it comes from this term. You look for the highest exponent on a polynomial. 7z to the 3rd minus 4z to the 2nd plus z. Yes, degree 3. Leading coefficient 7. Last one of these, 3x to the 5th plus 2x to the 2nd minus 8x to the 6th. Yes, degree 6. Leading coefficient negative 8. Okay, enough examples on that one? Okay. Okay, the next thing the author writes just gives you examples of polynomial functions. And we've already worked with a bunch of these this year. Like if they write it like an example, f of x equals 3x plus 5. Remember, f of x is the same thing as y, so y equals 3x plus 5. That is going to graph a line, so that is a linear function. What's the only type of line that's not a function? A vertical line, yeah. Anytime you have x equals a number, that's not a function. Okay, and another one, f of x equals 4x to the 2nd minus 7x plus 2. You look at the highest degree term. If that highest degree term is an x squared, and we did this in the chapter before, we got the parabolas. So those are quadratic functions. Some that you may not have worked with much, f of x equals, an example, negative 9x cubed plus 4x squared. If the highest degree term is a cube, then they call that a cubic function. And then the author also goes through this example. If you have f of x equal, and then in general, a x to the b power, that exponent's a letter b, a x to the b power, that is just called a power, where A and B are elements of the set of real numbers. They're not imaginary. Then this is called a power function because it's an x to any power. Okay. The author will also give you some problems like this on functions. If p of x equals 5, and a lot of times they switch it, instead of writing f of x, they write it p of x for polynomial function. So 5x squared minus 4x plus 1, and say they ask you to find p of negative 3. That just means in that polynomial function, everywhere you see an x, sub in negative 3. So you're going to put negative 3 in, and then you have to do the order of operations. Sub negative 3 in everywhere. So you would do the exponents first. So the negative 3 squared would be 9. So then multiply, you'd have 45. So we'd have plus 12, right? Plus 1. Yeah. And you'd end up with 4, 57, 58. And this is, when you look at that, p of negative 3 is 58, and that's our answer. But this is another way to write an ordered pair. Because remember, this is the x, the number inside's the x, and then this is the y. Okay. Final answer would be 58. Okay. Okay, the next part, the author goes through the general graphs for these polynomial functions. And this ties in a lot with what you do later on if you go into upper level math. So, a little separator there. These are the graphs of polynomial functions. And just in general what they look like. Okay. If they gave you a function f of x equals 3, okay, that's the same thing as y equals 3. What's that going to graph? Y equals a number, horizontal line, right? So that would graph a horizontal line at that y equals 3. Okay. And that is called a constant function. F of x equals a number is a constant function. The degree, if there is no x there, so it's really like x to the 0. So the degree is 0. Okay. If you have f of x equals mx plus b, that's like y equals mx plus b. What's that going to graph? A line, right? We don't know exactly what it's going to look like, but y equals mx plus b is going to graph a line. So that is called a linear function. And you can see the word line inside there, a linear function. And the degree, because it's y equals mx and it's x to the first, so the degree is 1. Okay, then the one we spent a lot of time on in that last chapter, f of x equals ax squared plus bx plus c. Your clue of what it's going to graph is you're looking at the exponents. Okay, if it's an x to the second, y to the first, you're going to get a parabola. Okay, okay, and that is a quadratic. If the highest a quadratic function, if that highest exponent, running out of room, if that highest exponent is a 2, okay, then it's a quadratic function. So you're really looking at these exponents. Okay, so the degree would be 2. It's a y to the first and an x squared. It's going to graph a parabola. Okay. Now, I'm not going to write down the whole equation on this one, Okay, but the highest exponent is going to be an x cubed. I'm not writing down the whole expansion. Okay, I'm not going to make you write it down. But an x cubed graph, okay, is going to look something like this. Okay, and it makes a difference whether it's a positive or negative number in front. Sometimes it will be turned around and look something like this. Okay, okay, but that one is a cubic function, and it's degree 3. Like I said, I'm not writing down the whole thing over here. Okay, just look at the highest degree term. Okay? The next one is an x to the 4th. If the highest degree term is an x to the 4th, it could look something like this. Okay, and that is called a quartic. It could open up or down, and the degree would be 4. How many times did that graph cross the x-axis? 4 times, right? It's going to cross on a quartic. It's going to cross an even number of times. It'll either cross 0, 2, or 4. Okay? On an f of x, go one more. If it's an x to the 5th, that one is a quintic. Okay, and that one is a degree 5. Okay, and look, something like this. 1, 2, 3, 4, 5. Cross 5 times. It's going to cross an odd number of times. Okay. So I just wanted to give you kind of an idea of the polynomials that you're looking at. Most of what we've covered is highest is the x squared, the parabolas. Okay. Now the author gets into the domains, the range, and what they call the end behavior. Okay. Put a little separator there. The domain. And the domain is the x values. The domain of any polynomial function is. If you go back and look at all of these graphs, all of them, go across left to right. On this, are we leaving out any x values? No. For the line, are we leaving out any x values? No. Parabola? No. 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 So the domain is all real numbers. For any polynomial function, the domain is all real numbers. So you're looking at, are they leaving out any x values? No. It's all real numbers. Then the author talks about end behavior. The end behavior is the behavior of the graph as, look up here, as x, read this, as x approaches, we're just going to use a little arrow for approaches, as x approaches positive infinity, or as x approaches negative infinity. So as x is getting really large or really small, what's happening to the y value? Is the y value going up to positive infinity or down to negative infinity? And I'll show you that on the graphs. Okay, and the degree and, I would say highlight that and. It's an and statement. The degree and the leading coefficient determine the end behavior and the range. Two things, the degree and the leading coefficient determine the end behavior and the range. Okay, now I'm going to go through a graph for the end behavior in general, the end behavior of a polynomial function. We're going to separate this into 4 boxes. Okay, this one, if the degree is even. So that means if your degree is like 2, 4, 6, 8, if your degree is even and the leading coefficient is positive. And the best example I could give you would be like y equals x squared. That degree is even. The number in front of the x is positive. How does that parabola open? Up. If it's a y to the first and an x squared and it's positive, it opens up. Now the end behavior, okay, and the author writes it, to me it's just backwards, but this I'm going to stick with the way the author's written it. The f of x approaches what as x approaches negative infinity. Now, this is all by looking at the graph. Look up here a minute. As x goes to negative infinity, as you go way out to the left, what's this y value going to? Shooting up to positive infinity. So this becomes positive infinity. Okay, and it's right here. As this x goes really small, this y goes up to positive infinity. So they would be looking at this as the answer. Okay? And f of x, what does it go to as x goes to positive infinity? As you go out far to the right, what's the y value going to? Positive infinity. So all you're really checking is it going up or down? Okay. Okay. So those would be your two answers. Okay. And that's for any even polynomial and a positive leading coefficient. That will always be true. Okay. Okay. If the degree is odd. Wait. Let's go down. Let's go down. Leave a space there. Okay, let's go down. Separate this into. Separate this. We'll go the other way. Go down here. Let's do degree even. Still even, like 2, 4, 6. But this time the leading coefficient is negative. What's that do to the graph? How's it open? Up or down? Yeah, so like if I did y equals a negative x squared, it's going to open down. Okay? So, yep. So as x, gosh darn it, I can't say, as x goes to negative infinity, y goes to negative infinity. It goes down, right? Don't you want to write this first? I want to write that first. As x goes to negative infinity, y goes to, as x goes to positive infinity, which way y goes down, right? So these are your two answers, negative infinity, negative. They both go down, okay? Okay, now let's go back up to odd. Okay, if the degree is odd and the leading coefficient is positive. Okay, so that's going to be like, look up here for a minute. It's going to be like graphing y equals x cubed. Your graph looks like this. It's going to go through the origin. It's going to be a curve like this. Okay? So as x goes to negative infinity, as x goes out here, what's this y going to? Negative infinity. F of x goes to negative infinity. As x goes to positive infinity, y goes to, okay, as x gets really large, what's y going to? It's going positive infinity up, right? Okay, and that works for an x to the third, an x to the fifth, an x to the seventh. Okay, let's do another one. This one is a degree is odd. At this time, the leading coefficient is negative. So that's like graphing a y equals a negative x cubed. Okay, look what that does to the graph. The positive one opens this way. Negative one opens this way. Yep. So as x goes to negative infinity, as x goes out this way, what's the y going to? Positive. So f of x, the y goes to positive infinity. As x goes to positive infinity, the y goes to negative infinity. Okay. Okay, and the last thing on this chart, the author talks about the domain and the range. Okay. So, and I would probably do that in a different color if you have it, or highlight it or something. Okay, let's go back up to this degree, even, and positive. The domain, what did they say the domain was in all of them? So the domain is double bar R. The range is all real numbers greater than or equal to the minimum y value. So you have to graph it and say, what's this minimum y value? So like on this picture, the range would be y is greater than or equal to 0, right? But it depends on what they give you for an equation. You have to graph it and then look at your y value. On this one, the domain would be all real numbers. The domain's easy. And on this one, are we leaving out any y values? No. So the range is all real numbers. All real numbers, all real numbers. Okay? Just double bar R, because we're not leaving out any y values. Okay, then go on the degree even and the leading coefficient negative. Domain, all real numbers. We're not leaving out any x values. And from what we did up above, what would this one be? The range, all reals, less than or equal to the maximum y value. So on this graph, this particular graph that I've got here, would be all real numbers less than or equal to 0. Okay, it's all the y values less than 0, less than or equal to 0. Okay, and then this last one, domain is, and are we leaving out any? No. So if it's an odd degree, they're both real numbers. Okay. Okay, the last part now. Be grateful you didn't have to read all this. Okay, real zeros. If they talk about the real zeros, it's the number of times the graph crosses the x-axis. And they may ask you to actually solve them. Where does it cross the x-axis? Okay. But if you look, you just count. Go back up to these graphs. Like if I said how many real zeros in the quartic graph. On this one, the way I've drawn it would be 4. I could draw it where it just crosses 0 times or twice. Okay. 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 So the real zeros, they're asking the number of times it crosses. Odd, degree, and we've already basically said it. The odd degree functions cross the x-axis an odd number of times. So if it's an odd degree, it's going to cross the x-axis like 1, 3, 5, 7, an odd number of times. Even degree, even degree functions cross the x-axis. Now there's an exception on this. The x-axis an even or 0 number of times. Because we had parabolas that did not cross, right? Drew them above the x-axis. Good. Good. Okay. So that's it for that section. That's a bunch.